manufacturers. Okay, now with that the server and cluster part is over. Now let's look at latency, throughput, and parallelism. Now what I mean by this is that you have to look at this in the memory operations. Okay, now here's the thing. Remember some time ago I told you about cache miss and RAM and stuff. Let's see what happens. Now let's say your okay, how is that? Yeah, let me change this to black. Now let's say this is your your processor, your cache, your RAM. Okay, now through your input devices you give a statement like a plus b. Okay, now what the processor will do is that will read the machine statement and realize, okay, you need variables a and b, so fetch a. Now a will be somewhere in your RAM, b will be somewhere in your RAM. First it will read step by step. First thing is at time t equals 0, fetch a. Now what happens is that this information will go to the cache. Now the cache will look at whether a is present. If a is not, it will go to the RAM. Okay, now let's say the processor at the time interaction that takes between a processor and cache is 2 seconds, whereas the time it takes between a cache and a RAM is like 50 seconds. Just for illustration purposes, but this is not the actual speed, just for illustration purposes. So at time t equals 0, the process says fetch a. Now the processor will try to look up for the data in cache. It didn't. Okay, so now it goes to RAM. RAM tries to get the value of a. So what happened is that it took 52 seconds to get the data, to find the data, and okay, now this data will come to cache, which takes another 50 seconds, and from there it goes to the processor again, so it takes 2 more seconds. So on the whole, it will have to fetch a, it took 104 seconds. Similarly, okay, so at t equals 104, this will fetch b. Now this will again take another 104 seconds. Now at t equals 208, okay, add a plus b. Let's say the addition process takes only 1 second. And now here's the thing. If you look at it, now this is what, if you look at it, just to fetch the data, just to fetch the data properly, it took about 208 seconds, whereas the actual addition operation took only 1 second. Now you might wonder, hey, this amount of numbering is crazy. Now, I'm not joking. This kind of thing can happen. What I mean is, like, the actual value I gave it for seconds is just for you guys to have a visualization of the speed. But if you look at this in machine cycles, this might be comparable. Okay, so this might be comparable. Okay, now with this example being with this example in syncing, okay, latency, what it says is that it refers to the amount of time taken to complete a given amount of work. So if you look at it, for this entire process to happen, it took about 209 seconds. So the latency of this addition process can be taken as 209 seconds. Okay, 209 seconds or some 209 seconds. Okay, now which includes all the delays and stuff. Next thing is throughput. It is in the same context as above, and when compared to memory operation, it is the amount of work that can be completed within a unit time. So here we can say it took 209 seconds for addition to complete. So this is actually the throughput of the system. Okay, if you're doing multiplication, it might be a little different. If you're doing division or something like that, it might be different. Okay, so depending on the operation, your throughput of the system will differ. And here's the thing, and that's what throughput means. And if you look at parallelism, looking at the same concepts, okay, parallelism is actually a process of increasing throughput and hide latency. Now let's see how this can be done. Now what I'm going to do, I'm just going to create a new page, okay, and then this is actually a single core processor. Now let me do this with a dual core processor or a dual core thread. This is processor 1, processor 2. Let's say both have a single cache, and then a RAM. Now P1 says P1 at time t equals 0 says fetch a. Now 2 second gap, 2 second gap, and this is 50 seconds gap. So to fetch A, P1 says to look for A in cache. Okay, it's not there, it's in the RAM. It's in the RAM. So it take 2 seconds to take. It's not in the cache, so it will take 50 seconds to get the data from RAM. So to fetch A, it will take 104 seconds. Fetch A, it will take 104 seconds. 104 seconds up and down. Okay. Now 104 seconds. Now instead of P1 doing the same, let's say P2, okay, the second processor or second thread of the second core of the processor at time t equals 0 understood it and says, okay, what kind of spelling am I using? Okay, this is fetch B. So this will take 104 seconds as well. Now addition, let's say processor 1 does the addition at t equals 105. Let's say both of them start together, you add A plus B. Now if you look at it, for this example, the latency is the time taken for the entire process to complete. This is 105 seconds when compared to 209 seconds over here. The throughput is doubled. Okay, the amount of here in this example, it take 209 seconds for the addition operation to done. Now with the same 209 seconds, you can almost do 2 additions over here. So the throughput is multiplied by 2. So throughput is twice, increased by twice. Okay, now how did this possible? It's because we did parallelism, meaning divided the instructions such that one processor was able to do one part of the job and other processor was able to do other part of the job by interacting with each other, and as a consequence your latency got reduced and your throughput increases twice. Without having any overload on any of the processors. Now this is what you call as parallelism. Okay, using parallel processing to increase the throughput and hide latency of a program, hide latency in the program. Okay, now that's a simple explanation. Now in the next tutorial, I will be explaining guys about the temporal locality and spatial locality, which comes together with latency, throughput, and parallelism. Okay, thank you guys for watching, and see you guys next time.